Okay, so the issue at hand is that the syntheses that we're going to get are going to get to be pretty complicated. And so when they get complicated, we're going to oftentimes utilize something called retrosynthesis, right? So put simply, this means we're going to look at the end first, okay? And we're going to find that if we look at the end first, it'll oftentimes narrow the field substantially and make things a lot easier for us, okay? So it's going to take some getting used to. So we're going to still start with the same first two questions. Question number one is the carbon skeleton changing, and is the functional group changing and or moving? Right. We're going to analyze the structure of the reactant and product, and we're going to say what functional groups are we dealing with. So we're going to make a list of all those things. All right. So number one is the carbon skeleton changing in this particular compound. So I recognize this right here, and I'm not going to worry about that. It's not going to be unusual that we'll have something like a little crow's foot right there that makes it easy for us to just count otherwise. So I'm not going to worry about counting all those. But I'm going to go here and I'm going to say carbon 1, carbon 2. And here I'm going to say carbon 1, carbon 2. Okay, so far so good. There's no change in the carbon skeleton. Now, is there a change in the functional group? And yes, the answer is of course, right? We have an alcohol here and we have an alkyne here, right? So definitely there's a change there. How do we get alkynes? Well, we get alkynes by elimination. What do we get? How do we get rid of alcohols? Well, either by substitution or elimination, right? So let's come over here again. We're gonna come here and we're gonna say, let's think about ways that we get to an alkyne. This is retrosynthesis. So we're gonna start at the end first. Okay. So if we start here at the end first, how do we get alkynes? Well, we get those through elimination, right? Well, one way we can eliminate this, I think I've got this in the next slide, is we can eliminate we can do a Hoffman elimination here, right? So if we do a Hoffman elimination, 1, 2, right? That'll give us boom, boom, an alkyne right there. This is Hoffman, okay? We could do a Zaitsev elimination here, right? Boom, boom, right? Or we could do a Hoffman elimination here, right? If we do a Hoffman elimination here, and we're going to eliminate this one first, and then this one, right? Now, it turns out this vicinal halide is the only one of these we know how to make. We could do any of the three of these. Here's a geminal dihalide. Here's another geminal dihalide. But this is the only one we know how to make, right? So, or at least I should say, the only one we have a simple access to making. How do we make a simple vicinal dihalide, right? So what we're going to do now is we're going to assume we've done that one. We've made this step. We've made this from a vicinal dihalide, right? By simply doing a excess elimination. Okay? You recognize that? Okay. And then we're going to say to ourselves, how do we make that? Well, wait a second. This can be made from an alkene, right? So we can step our way back one step at a time. So this, right, the vicinal dihalide can be made from an alkene. All right. So, and all we got to do is have bromine for that. So we write that in there. You see that? So I again, starting at the very end, I've already got this step in here. Then I say to myself, I want to make a vicinal dihalide. All it takes is bromine and carbon tetrachloride, right? Now, how do I get from here to here? And I go, oh, you know what? That's only one step. I remember how to do that. I do that with tosyl chloride and pyridine. Make it a good leaving group first. Remember that? And then I get a strong non-nucleophilic base, right? A strong non-nucleophilic base. And you have to recognize both of these, by the way. If you're doing synthesis, you can choose whichever strong non-nucleophilic base you want. But if your test or your exam or your quiz gives you DBN, you've got to know it's a strong or if it gives you DBU, you've got to know it's a strong non-nucleophilic base, right? So again, we make it a good leaving group with tosyl chloride first in pyridine, and then we give it a strong non-nucleophilic base, and that's it. Look at that. Step 1, which is really 2 reactions. Step 2, and step 3, which is really 2 reactions, right? So we have our synthesis, and we did it by going backwards. And this is called retrosynthesis. So we're going to put it all together, and it's going to look like this. We start out with tosyl chloride and pyridine. we give it a strong base, terbutoxide, to make it, it doesn't matter, just a strong base of any kind. I don't even think I used terbutoxide in the previous one, did I? Nope, DBU or DBN, right? But I could have used terbutoxide. So here I use terbutoxide. In here, I dihalogenate that, right? And then I do a double elimination, right? And I simply add water to make sure that in the end my acetylide is protonated. Okay, so now I guess the last thing you should do is you should make sure everything's correct. Go through and write the product of this and that, right? And then give it that, then give it that. Go through and check it and make sure you're correct. All right, so that's an overview, pretty fast overview of retrosynthesis, but we're going to see it again.